welcome to our physical sciences session. My name is Themba Ncube. Today we are focusing our attention on solving circuit problems. So we're going to take a discussion on, the approach to responding to typical examination questions, and also, share some of the strategies, that one may actually make use of in terms of, responding to questions. We'll also try and, zoom into the multiple choice and some of the dynamics, things that one has to look out for in as far as the multiple choice is concerned. Right. We have done by this time, the different aspects of, circuits, in terms of power, the Ohm's law, and it all comes together if we have the necessary understanding so that we can be able to apply the knowledge that we have gained in responding to, problems. Okay, right. Okay, some of the concepts that I would look into or apply in as far as problem solving have to do with understanding the Ohm's law, which talks about the relationship that exists between current as well as voltage at constant temperature. But also remember that this is in the context of electric circuits, which can either be a parallel circuit or a series circuit. Now, if you talk of a parallel circuit, this has to do with current dividers. Okay, the current dividers, very important. Understanding, as well as potential dividers in as far as the series circuit is concerned. Okay, so these are the main ideas. So if we are to apply this knowledge, this has to come to the fore. But also remember, we need to understand what power involves in terms of energy conversion per unit time, and power has implications on the cost of electricity that we use in our homes. Okay, right. These are some of the concepts that we dealt with in one at a time, but at some point we need to create these very important links between these concepts so that we show some understanding. Let's focus our attention now on the formula sheet. So the data sheet, we are saying it's going to be provided to you, during the assessment time or when you write, your tests, your exams. You need not to memorize all the formula because there's a whole lot of them. Okay, so just understand that, okay, a particular question has to do with a certain concept, and these are the relevant formulae, the mathematical equations that you'd want to make use of as part of problem solving. So it's important to be able to identify the formula, copy it as it is given, okay, do the necessary conversions if that's the case, before doing the substitution, and then do the, the calculation using a scientific calculator. Make sure that, again, the SI unit, which is correct, is attached to that value that you are calculating. And in some cases, there is a need that you interpret your answer because we need to put, the science behind the numbers. And beyond that, we have a multiple choice scenario. Okay, there's a lot of perceptions in as far as the multiple choice is concerned. But what is important about multiple choice is that we need to allocate, a decent amount of time, reasonable time, to respond to those questions, because not all the questions require the same effort, in terms of arriving at the correct answer. Never mind, we are given, 4, possible options, and then now we need to identify the 2 distractors so that we get that out of the way. Then you'll be left with 2 options. In most cases, you choose the correct answer, thereby, enhancing your chances of actually getting it correctly. Right. Now, so the data sheet is a very important tool in terms of the conceptual understanding. So you can immediately tell that this formula has to do with current, which from this we can say, okay, current is the rate, of flow of charge. Okay, is the rate of flow of charge. Okay, so we are simply reading it off mathematically. That's our Ohm's law there. Okay, so we need to be familiar with all this. We know this is the formula that we use to calculate total resistance in a series circuit. Okay, while the other one is for a parallel circuit. All right. Okay, and then the issue with energy, okay, which you would have discussed in as far as power is concerned. This has got to do with energy. You know, work is energy, energy is work. When work is done, energy is converted from one form to the other. And then these are the variations in terms of the power formulae, okay? So you'd identify the correct formula based on what you are given, okay? Now we look at a typical multiple choice problem which reads as follows: which one of the following is equivalent to 1 volt? So the idea here is that, you know, we're looking at the understanding of the quantities in terms of the SI units, okay? So let's locate the SI unit volt in terms of its quantity. This has to do with potential difference. This has to do with potential difference, okay? So when we talk of potential difference, we are talking of voltage, okay? And what do we know? We know that V is equals to W over Q. So this is actually, what are we saying? We are saying that voltage across a device is the work done per coulomb of charge. So the work is measured in terms of energy in joules, while the charge is in coulombs, okay? So we can immediately say that a volt is equals to 1 joule per coulomb of charge. So we are able to immediately identify the correct option. But then the other option, joule second, it's something else. This is like energy multiplied by time, of which we don't have such. And then joule per second, maybe this is what we call the watt, which has to do with power. So this is out, that is out, and then B and D are actually saying the same thing, because 1 watt is equals to 1 joule per second, right? So that's how you would actually approach the question. And then we've got another one which says, in the circuit below, a battery with an EMF E. So we are given the EMF, okay, which is the maximum energy that can be provided by the source, which is the battery in this case, for every coulomb of charge. And then we're told that the battery has got negligible resistance. So when the resistance in a battery is negligible, what does it mean? It means the EMF, okay, is actually equals to the terminal potential difference, okay? Okay, what does that mean? Because the battery has negligible, or a very small resistance that we can ignore, it means the maximum energy that this battery can provide is actually equal to the terminal potential difference, which goes to the external circuit, okay? Now, these two are connected to 2 resistors in parallel, okay? The resistance of one resistor is double the resistance of the other. This is a very useful piece of information, okay? What are we saying here? We are saying that the 2 resistors, the other one is R, the other one is 2R, okay? So if that's the case, it means one resistor is actually double the other one in terms of resistance. And then the question says, what are the ammeter readings and voltmeter readings in this circuit? Okay, we are told that the current that passes through the ammeter is I, right? Now, the I, which is the total current, which is the current that passes through 2R, because this voltmeter will actually measure I, okay? Is it fine? Because you think of it in terms of, okay, when the current gets to that point, it is split, the other one goes to 2R, the other one goes to R. And then the question says, what are the ammeter and voltmeter readings? Okay, let's understand something, okay? If I goes through, current I goes through that ammeter for 2R, how does the current that go through R compare to that goes through 2R, okay? Remember, from the Ohm's law, we know that current is equals to V over R, okay? So what else do we know? We know that V across R, okay, is equals to V across 2R. Why? Because these 2 resistors are connected in parallel. So V across 2R is equals to V across R, okay, because it's a parallel circuit. Now, if the resistance of 2R is double that of R, what does it mean? It means R will receive more current than the current that goes through 2R, okay, because 2R is double R, okay? That's another way of actually saying it. So the current that goes through 2R, okay, is equals to I, right? and then the current that will go through R, it must actually be double the current that goes through 2R, because R is less resistance than, actually is less resistance than 2R, okay? Now, in terms of E, we know that the potential difference, which goes, the potential difference across 2R is equals to R, because the two resistors are in parallel. So obviously, if it says double, it means option A is out. Why? Because it says double while E remains constant. Okay, so that is also out. So we are left with option B and C, right? And E and D rather. Okay. Now let's check. If the current that goes through I, 2R is I, it means the current for R must be double that. Okay. So if the ratio, total ratio is 3, then the current for the ammeter reading 2R should be actually a third of that, because the ratio is 1:2, okay? It's actually 2:1 if we say 2R is to R. So it's 2:1. So the one that goes through 2R will be 1/3 of the total current in the circuit, all right? Now, which means our solution in this case becomes option B. Okay, this is actually the current that goes through, this is the current that goes through R, okay? Right, and then the last one, multiple choice for the segment. In the circuit alongside, the power dissipated by the 3 ohm resistor is P, okay? So the power here for the 3 ohm resistor is P, right? And the power dissipated by the 6 ohm resistor is what we want to understand. Okay, what do we know about these two resistors? We know that the voltage across 6 ohms, okay, let's call this V2, okay, is equals to the voltage across 3 ohms. Why? Okay, because we're saying V across 3 ohm is equals to V across 6 ohm, okay. Why? Because it's a parallel circuit. But the current that goes through 3 ohms is actually double the current that goes past 3 ohms. Why? Because this parallel circuit is actually a current divider. So the smaller the current for the same voltage, you know, the smaller the resistance for the same voltage, the greater the current. So the formula for power says P is equals to I squared R, okay? So if it's I squared R, if more current goes through 3 ohms than the 6 ohms, or even if we look at it in terms of P, is equals to V squared over R, okay? Now you'd realize that the V1 is equals to V2, okay? Based on that parallel combination of resistors. So the one that has got the smallest resistance will have the greatest power for the same voltage. So if the 3 ohm resistor is P, it means for 6 ohms, it should be half that, because the ratio or the proportion of these two resistors is 1:2. So it means the 6 ohm resistor will dissipate a power which is actually half, which takes us to exactly that. So you may realize that not all multiple choice questions ask the same level of understanding. In some cases, you have to apply a number of concepts like we've done with the previous one. So you need to take that into account and also try and best manage the time that you have, which you allocate for your multiple choice problems. When we come back after the short break, we'll look at the typical structured or long questions which you'd normally find in your section B. Let's take a short break for now. Welcome back to our second segment. We're still looking at solving circuit problems. Now we want to focus our attention on questions that are structured, the long questions that we typically find in section B. We'd also share some tips in terms of how you approach the question. But also very important, when you read the background or the context of the problem or the question, the scenario, make sure that you read it with an intention to understand before even looking at what the questions are really asking you. Understand first, highlight the keywords, you know, because for every information that you are given in a long question, there is always that part that I'd want to think of as a catch, you know. Once you get the catch in a question or something that's unique about that scenario, then you are able to appropriately use the correct, you know, approach or method of solving that particular problem. Let's look at one example here. It says here, the circuit alongside, that's the circuit that's provided, consists of a 6 ohm and 15 ohm resistors that are connected in parallel. So the two resistors that are given are the 6 ohm and the 15 ohms are in parallel, okay? Now a resistor of an unknown resistance R, okay, there is the resistor of unknown resistance R, okay, is connected in series, okay? So R is connected in series while the 6 ohm and the 15 ohm are connected in parallel. Now the resistance of the battery and the connecting wires can be ignored. What does this tell us? It tells us that the battery and the conducting wires have negligible resistance, okay? The total power dissipated by the parallel part of the circuit is 50 watts, okay? So the power for both circuits combined, sorry, for both resistors combined, which is the 6 ohm and the 15 ohm, is actually 50 watts, okay? Now the first question says, define the term power, right? So when you talk about power in the context of electric circuits, okay? If you talk about power in the context of electric circuits, what are you talking about? Power is actually the rate, okay, of energy transfer, energy conversion, or energy, you know, transformation, energy transformation, okay, in a circuit, okay, right. So even if we go back to our data sheet, you'd realize that this is the power definition that we talk about. So W is energy or work, all right? Right, and then we also have time, okay? And then we talk about, when we talk about time, we're talking about the SI unit, which is the second. So the data sheet becomes a valuable, you know, resource in terms of that, okay? So we understand that power is the rate of energy transformation in a circuit, or work done, because when energy is transferred, work is done. It could be, and then we also go on and say work is equals to change in energy. So work is energy, energy is work. So this is the main concept regarding work and energy. But again, we say that we can say P is equals to W over delta T, right? Okay. Now, the resistance of the battery is ignored. Now, the follow-up question says, calculate the effective resistance of the parallel combination, right? If you look at that, we are talking about these two resistors, okay? What is their combined resistance, okay? Again, if we go back to our data sheet, okay, you'd realize that for a parallel circuit, this is the formula that you need to make use of. But if there are two resistors in parallel, we can use even the product over sum, okay? So R parallel, okay, is equals to, we have the product, let's call this R1, okay, and then this one R2, 15 ohms R2, okay, and then we would have, let's say, R1 multiplied by R2 divided by R1 plus R2. So this is actually applicable when only two resistors are connected in parallel. But if it's a combination of more than two resistors connected in parallel, this formula may not be used, okay? So we've got R parallel, okay, is equals to 6 multiplied by 15 ohms, okay, divided by the sum of those two, 6 plus 15, right? Now, there's something that you need to realize with the parallel combination of resistors. The more resistors we connect in parallel, the lesser the equivalent or the effective resistance of that combination. So in this case, the smallest resistance is 6 ohms, okay? Now, if we calculate or determine the total resistance or the combined resistance of the two. Actually, what must happen, the combined resistance must be less than 6 ohms, which is the smallest resistor. That's one way of verifying that. Okay, so if we go to our calculator, then it follows that we have, okay, it's a fraction. Okay, R1 is 6 times 15, okay, and then at the bottom, at the denominator, is the sum of those two, 6 plus 15. Okay, so our effective resistance is 30 over 7, which gives us 4,29 ohms. And 4,29 ohms is actually less than 6 ohms, which says then our answer is correct in this way. That's one way of verifying. So it's 4,29. Okay, so this is RP is equals to 4,29 ohms. Okay, right. Let's go to the next question. The next question says, calculate the potential difference across the resistors in parallel. Right. So this question is actually 3 marks. So this is what I would want to think of as a routine calculation. Right. So we are given the power, okay, of the parallel combination. So if we are to do that, we can use the power formula because we've got the resistance of the parallel combination. And what are we looking for? We're looking for the voltage. So the formula is P, okay, is equals to V squared over R. So this is R parallel, okay, that we're using because it says for the resistors in parallel. Okay, so the 50 watts is for the combined power rating of the two resistors, which gives us 50 watts, okay, which is given, then V squared, the resistance that we got for those two, we are going to use the solution from which is 4,29, right? So we'll do that substitution, 4,29, okay? So that's the resistance. So we're looking for voltage. Okay, remember that is V squared. Okay, now we have done the substitution without even trying to isolate V. Okay, so we'll do the calculation so that we get the magnitude of your voltage across that parallel combination. Okay, so we are saying on our calculator we have got 50 multiplied by, we've cross multiplied with the resistance, which is 4,29. Okay, 4,29. Okay, that gives us that value. But remember, this is equal to V squared. Okay, so for us to get the V, we need to find the square root of that value. Okay, whatever that value is. So our voltage across the parallel combination of resistors is equals to 14,65. Okay, it's going to be 14,65. 14,65 volts. So we can think of this as V parallel because that's what the question wants from us. Okay. Now, in the next question, they want us to determine the current passing through resistor R. Okay. They want us to determine the current passing through resistor R. Right. So what do we know? We know that the total current passes through, the two resistors, which is the 6 ohm and the 15 ohms, or the total current rather is split between those two. So if we can find the total current in the parallel combination, it's exactly equal to the current that passes through R. Okay, so we are saying that the total current, which is the main current, is equals to V parallel divided by R parallel. Okay, because it's a 3-mark type of a question. It's the formula in this case, which is the Ohm's law, the substitution, and then the correct answer. So the total current is the current that passes through R, okay, which is current through R, okay, is equals to our V parallel. We managed to get a value of 14,65 volts, right? So that's 14,65, okay, divided by R parallel. What did we get for R parallel? We can quickly verify that value. For our R parallel, we get 4,29 ohms, okay? 4,29 ohms, 4,29 ohms. So this is the current that will go through resistor R. So that was the thinking. Now we go to our calculator, right? We've got 14,65, okay? We divide that by the effective resistance of the parallel combination, which is 4,29. Okay, it will give us the magnitude of the total current in this circuit, which is 3,41 amperes, right? So that gives us 3,41 amperes. This is the total current. Okay, so this 3,41 amperes is split between 6 ohms and our 15 ohms. So, but it's all the current that goes through resistor R. So it's very important for us to take note of that. Right. Okay. Moving along. Now, the same circuit, we're still looking at the same setup. It says here again, the total power is still 50 watts. Okay. Now, the switch in the circuit is now open. This is the switch. Okay. What does that imply? If we open this switch, let's call it switch S for now. If switch S is open, okay, what's going to happen? It will mean that there will be no current flowing through the 15 ohm resistor. So the only resistance that we have left now is actually the 6 ohm and R. Okay, so we have got two resistors that will be connected in series. Okay, all the current passes through R and all the current passes through 6 ohms. Now, let's go back in terms of understanding the parallel circuit. The fewer resistors we have, or no resistors we have in parallel, the greater the effective resistance in the circuit, okay? And how does that affect the current in terms of the Ohm's law? Maybe that's the kind of thinking that one must assume. In this case, we are saying, okay, if we open switch S, okay, we won't have a parallel combination of resistors. It means, number one, let's appreciate that the total, resistance in the circuit increases. Okay. So if the total resistance in the circuit increases, what does that mean in terms of the current? Okay. Total current will decrease. So we're saying the total resistance increases. Very important to mention that it increases, not just changes. Okay, it increases. So we know from Ohm's law that current and voltage are actually, directly proportional. So if the current decreases, that will also have an effect on the voltage, because V is directly proportional to I. Okay, so a decrease in current will be accompanied by a decrease in voltage. So the voltage will decrease. Okay. So if the voltage decreases, it's based on the Ohm's law. So in other words, if we are to work backwards, okay, we are saying that the voltmeter reading V will also decrease. Okay, based on the fact that removing the 15 ohm resistor from the equation says to us that the effective resistance in the circuit will increase. That will effectively decrease the total current, meaning also the voltage will have decreased, which justifies our choice in this case. So these kind of problems that have to do with the, thinking and applying, they require you to understand, each part of the question clearly. Because when we open the switch, how does that affect the total resistance? Now, if resistance has increased, how does that affect the current? And you are always supposed to respond to these, type of questions that involve explanation. You need to use, simple facts. You don't write a long essay. Just be straight and short and brief to the point, because it says for any case, a question which requires, explanations, you need to be brief on that. Okay, right. Okay, and then this other question says a geyser labeled 2,000 watts. Okay, on average uses daily 5 hours. It's used daily for 5 hours. The cost of electricity is 80 cents per kilowatt. Okay, calculate the cost of electricity for using the geyser in a 30-day month period. Okay, now we know that when we talk about the energy consumption, we are saying that the cost of using electricity is equal to the unit price okay, which in this case we are given multiplied by the kilowatt hour, okay? Right, so this is what we have here. And when we talk about a kilowatt, we are saying that 1 kilowatt is actually equals to 1,000 watts, okay? So energy consumption is always in kilowatt hour, okay? So if we have got 2,000, it means there are 2 kilowatts, okay? So in this case, we are going to say cost is equals to, that's the 2 kilowatt, but the price is given is 80 cents, okay? 0.80, which is 80 cents. How many kilowatts are there? It's 2. The 2 comes from the 2,000. So 2,000 watts is 2 kilowatts, okay? Multiplied by, you know, the amount of time that you use per day, and how many days do we have in that month. If per day is 5 hours, it means we've got 35 hours in a 30-day month. Okay, so then our cost becomes, if we can go to our calculator, you'd realize that we have, in this case, it will be 0.8, okay, multiplied by the 2 kilowatts, which comes from the 2,000 watts, multiplied by the 5 hours that is used, the duration per day, and then in 30 days we multiply it by 30, okay? So this is actually 240. Actually, this is in rands. So this value is actually in rands. So the cost for using it is actually 240 rands. Okay, it's 240 rands per month. So that's the cost of using the geyser for that period of 30 days. Okay, so these are some of the questions that you must expect in terms of circuits, you know, energy consumptions, which has a lot of application, which makes us to think about the ways of saving, you know, electricity given the current scenario that we find ourselves in. In the next segment, we'll look at more circuit problems and explore the Ohm's law and see how these concepts comes together. Let's take a short break for now. Welcome back to our third and final segment. We're still looking at solving circuit problem. Now we want to focus our attention on another circuit that obviously is different from the previous one. And as we've mentioned earlier, that every scenario or every situation is unique in its own special way. So be careful with the familiarity thing to say, oh, I've seen this before. There is always something that would differ from what you are familiar with. But read the question with an intention to understand it before even attempting to respond. Now let's look at the last question, which says, in the circuit alongside, okay, the circuit is given, the resistance of the 6-volt battery and the connecting wires are negligible. So it means that this 6 volts is actually the EMF of the battery, okay? It's actually the EMF, okay? Because we are saying that the battery has negligible resistance, so it doesn't offer any resistance to the current flow, okay? Switch S is closed, okay? There is our switch S. If the switch S is closed, we are told that the current in the 6 ohm resistor is 0.6 amperes, okay? So the current that goes to this resistor is equals to 0.6 amperes, right? So is that the total current? Definitely not, because part of the total current goes to the 4 ohms, okay? And immediately we are thinking, oh, okay, 4 ohms is lesser than the 6 ohms. It means it will receive a current that there's some current that is greater than that of 6 ohms because it has lesser resistance. In other words, we are saying current for 4 ohms is greater than the current for 6 ohms. Why is this true? Because V across, 4 ohms, okay, is equals to V across 6 ohms. Why? Because the 2 resistors are actually connected in parallel, okay? The only thing that's going to differ is the current, because we're saying this parallel combination of resistor is actually a current divider. Now the question says, calculate the current passing through resistor X. Okay, we want the current that passes through resistor X, right? Okay, so now the question says to us, calculate the current passing through resistor X. we know that the current that passes through resistor X is actually the total current, right? So if that's the total current, which is equals to, so the current for resistor X is equals to the current that goes through 6 ohms, which we have, plus the current that goes through 4 ohms. Why? Because these two are actually connected in parallel. They are current dividers. So we can find the voltage for 6 ohms, which is equals to the voltage across the 4 ohms, right? So V across 6 ohms is equals to the current across the 6 ohms, okay, through 6 ohms multiplied by the resistance, okay? So the current for 6 ohms is 0.6 multiplied by 6, okay? This will give us typically, which is our V1. V1 is actually the V parallel, okay? So if we go to our calculator, okay, 0.6 multiplied by 6, right? It gives us that value, which is 3.6 volts, right? So V1 is equals to 3.6 volts. In other words, V across 4 ohms is the same as V across 6 ohms, which is V1, right? Now, we can then find the current that goes through 4 ohms. So the current that goes through 4 ohms, okay, is equals to V1, okay, divided by R, okay? So our current for 4 ohms, okay, the current that goes through 4 ohms is effectively equal to V1, we've managed to get that 3.6 divided by 4, right? So the current for 4 ohms takes us to, if we go to our calculator, right, that is 3.6 divided by 4, right? This is 0.9, right, which is the current that goes to 4 ohms. And you'd realize that 0.6 is for 6 ohms, and then 0.9 is for 4 ohms. And it says to us 4 ohms has lesser resistance. That's why it gets greater current. So the total current that goes through X is equals to 0.9 plus 0.6, which means the total current for X is equals to 1.5 amperes. So this is typically a multi-step type of a problem. Right. Let's go to the follow-up question, which says calculate the current passing through the 4 ohm resistor. We've actually done that, okay? There are many ways to do it. So the current that goes through the 4 ohm resistor is actually equal to the voltage across the parallel combination, which is the same as the voltage across 6 ohms, which is actually V1, okay? Divided by that resistance. So we got that resistance, that voltage to be 3.6, okay? So that voltage is 3.6. So this is 3.6 volts, okay? So if that is 3.6, which is exactly the voltage across 4 ohms, all right? Okay, so this is equals to 3.6 divided by 4, okay? This is what gives us the current that goes through 4 ohms, which is equals to 0.9 amperes, right? So it's a simple thing. If the total current is equals to 1.5 amperes, and then the current that goes through 6 ohms is equals to 0.6 amperes, then the current that goes through 4 ohms is equals to the total current minus the current that goes through 6 ohms, okay? This will give us exactly that, right? Okay, moving along, now we want the resistance of X, right? Resistor X is of a known resistance, but we know something about V2, okay? Now we know that the total voltage in this circuit, okay, V total is split between V parallel, okay, plus Vx. So this V parallel is your V1. So V1 is the voltage across the parallel combination of resistors. So if the battery has negligible resistance of 6 volts, this is the terminal potential difference, which means it's 6 is equals to, we've calculated V parallel, which is 3.6, right? And then plus V across X, okay? So V across X will actually be 2,4 volts, right? So that's what we know already. But we want to calculate the resistance. We know the total current passes through resistor X, okay? So Rx is actually equals to V, okay, 2 divided by the total current in the circuit, okay, which goes through resistor X. So Rx reduces to, what is our V2 in this case? Our V2 is 2,4, okay, divided by the total current in the circuit, which is 1,5, okay? Then we can take that to our calculator. Okay, it's a 3-mark question, formula substitution and answer. So it's 2,4 divided by 1.5, okay? Okay, then we need to divide that. Okay, let's delete. Divided by 1,5, okay? It's actually 1.5, okay? Make sure that the values that you enter is correct. So the resistance of resistor X is actually 1,6 ohms, right? So resistor X is a resistance of just to confirm that, 1,6 ohms, right? 1,6 ohms. That's the magnitude of resistance, right? Okay, so there are also many ways of actually doing this, okay? But this is one of the obvious ones. And then the last question says the 4 ohm resistor gets hotter, okay? Think about energy, okay, than the 6 ohm resistor after a while, okay? Explain this observation. Why does the 4 ohm resistor get hotter? We have discovered that if 2 resistors are connected in parallel, the one that has got the smallest resistance receives the most current. As a result, this if the 4 ohm resistor and the 6 ohm resistor were light bulbs, which one of the two will burn brighter? Actually, the one that's going to burn brighter is the 4 ohm resistor. What does it mean? It means that this 4 ohm resistor actually transforms a lot of electrical energy compared to 6 ohm per unit time. As a result of that, it gets hotter and hotter. This is a question that actually relates to something about power. So think about power in terms of I squared R. So if you're saying the power that is dissipated by a device equals to the square of current times the resistance. So remember, the one that has got the smallest resistance will actually burn brighter, meaning that it transforms a lot of electrical energy into other forms per unit time, which explains why the 4 ohm resistor will actually get warmer quicker than the 6 ohm by comparison. Okay, so these are some of the the concepts as an example that we used in trying to address how we solve problems. We certainly hope that the discussions are fruitful and you try and locate the concepts and understand how these ideas that we discuss in isolation, how they come together, and we can apply the right strategies, use the data sheet, also get some confidence in as far as answering the multiple choice, because this requires a lot of practice, until we kind of get used to it. So because of time constraints, that's all that we have for today. From myself, it's cheers and bye-bye for now.